Okay, exercise step 132, physics 11, question 5. This has got a three-part question to it. Looks intimidating, but it's not too long. A car moves at 12 meters per second and coasts up a hill with a uniform acceleration of negative 1.6 meters per second squared. So we see a negative acceleration. That means it's the vehicle is actually slowing down because it means acceleration is in the opposite direction of the movement of the vehicle. That's what the negative sign always means. Opposite direction, or opposite direction, basically. So part A of this question says, well, what is the displacement after 6 seconds? And B is, what is this displacement after 9 seconds? So just changing the T. And notice anything surprising, try to explain. So a quick look at what we've got here. I see that we've got, we're moving at 12 meters per second. And we're coasting, so we're slowing down because we have this acceleration of negative 1.6. And by the way, 12 meters per second would be our VI in this case. So what is this displacement after 6 seconds? Well, let's write down our information first, see what we got to work with. So we got a VI, 12 meters per second. We have an acceleration, negative 1.6 meters per second. We have a T. Whoops. Get back there. We have a T1, which is equal to 6 seconds, 6.0 to be precise. We have a T2, second time, 9.0 seconds. And we're always just solving for D, displacement. So we have a D1. We also want to know what the D2 is. Well, that's what I want to know. So here we go. So part A. I want to know, let's change the color up a little bit here. Part A, we have a V, we have velocity, initial velocity, an acceleration, and a T, time. It takes us right to this displacement. On you. This is our VIT plus 1/2 AT squared. And this is, this is fine as long as we're not solving for T. And you can solve for T as well, as long as your VI is 0. And your VI is not 0, you got a T and a T squared both in there. It's tough to solve. Okay. We're solving. This will be D1, hey? So D1 displacement 1. So our VI is 12 meters per second. And our T is 6 seconds. It's 1/2. Our A is negative 1.6. And T is 6, right? 6. Only it's squared this time. Okay. So 12 times 6 is 72. Plus 1/2. Let's take this one step at a time. Negative 1.6 times 6 squared, which is 36. Okay. Okay, so that's, come here, you, stop that. It's equals 72 plus, let's do the math here. We've got 1/2 times 1.6 times 36, which is 28.8, negative 28.8. So we add that to 72, and we get 43.2. meters is displacement 1. Sig figs, we go back and look, we see we only have 2, so in fact our answer then for part A is displacement equals 43 meters. Complete. Write your statement, right? The vehicle has traveled 43 meters after 6 seconds. Okay. We need more space. Let's go with part B. Part B said, what about T2 is 9 seconds. Okay. So we can use the same formula, because everything else is the same. So D2 is equal to velocity initial, VIT, plus 1/2 AT squared, in which, what was velocity initial again? 12? 12 times T, this time is 9, plus 1/2, negative 1.6, times 9 squared. So here we have 12 times 9, is that 108, plus 1/2 times negative 1.6 times 81. So calculator time, 108 minus, what's it going to be? I've got 1/2 times 1.6 negative times 81, just minus 64.8. Which just comes out to 43.2. And 2 sig figs, so displacement 2 in fact is 43 meters. Good. Okay. Part C. One more time. Part C says, okay, anything surprising? Well, you notice that displacement 1 is equal to displacement 2, which is equal to 43 meters. In other words, the distance from where it started to 6 seconds later was 43 meters, but the distance from where it started and to 9 seconds was as well 43 meters. How can you explain what's going on? Well, in order to do that, we need to go back to the question. It says it's coasting up a hill. So here's our hill. Okay, and here's, let's say this is our 0 location, and here is our 43 meters. So what I can visualize happening here, now let's just change the color for the car, make him green, I guess, going up here. The car goes up, and after 6 seconds he reaches there. But he must not have stopped yet. He must be still coasting forward. Just alter this a little bit. He's still coasting forward till he comes to a complete stop, and then he starts coming back down. And lo and behold, so this must take 3 seconds. So in a total of 9 seconds since he left point 0, he is again 43 meters from his point 0, or his displacement. Let's show this as a different color maybe. So our displacement itself is only from here to here, right? Delta D. So this is how we can explain that after 2 different time intervals, he's still at the same spot, because he's coasted up the hill, 6 seconds he's there, but he keeps on coasting until the car comes to a stop and comes back down, and 3 seconds later he's back to 43 meters again. If we wait long enough, his displacement will actually be 0, because he'll eventually work his way all the way back down the hill here. Good old gravity bringing him down. So that's what we can say, that yeah, at some point it stopped beyond 43 meters of coasting back, and a total of 9 seconds later he's back to that same point. Maybe even add a little bit of a picture here to help explain what you're saying. Picture's worth a gazillion words in my mind in physics. Question is complete. Anybody notice my unit error in question 5, that I didn't put meters per second squared for my acceleration? If you noticed it, kudos to you. If you didn't notice it, go back and fix your own. We're on 132, question 6 now. A car is accelerating at a constant rate, so the constant acceleration, from 15 meters per second to 25 meters per second, and during this time period he travels 125 meters. How long does this take? Okay. You get a funky color here. So first of all, we have acceleration is constant. It's worthy of note. We've got a velocity initial, velocity final, we've got a displacement, and we want to know time. Okay. Let's get these jotted down. What we know, VI equals 15 meters per second. Velocity final, VF, is 25 meters per second. Displacement is 125 meters. And T, well, we are unsure. And acceleration is not given either. But this is really what the question is asking. How long? Let's take this. Duration of time. Okay, so you need to check this out, hey? I'm going to look at our formulas. Take a tour. See, first of all, if we can get away with no acceleration. Is there an equation that has displacement, velocity initial and final, and a t in it to solve for? If there is, we're good to go. And in fact, there is. Put it down here at the bottom, I guess. We have a displacement formula that says take VI, initial velocity, and add it to your final velocity, divide it by 2, and multiply that whole thing by time. Okay? And we're ready to rock and roll. So let's just plug it in. We know delta, our displacement is 125 meters. VI is 15. VF is 25. Divide by 2. Multiply this whole thing by t. Okay. Well, I would say we got to get this bracketed thing away from t. So I think if we can solve everything inside this bracket, it would make things a lot easier. So let's go for it. 15 plus 25 is 40. And divided by 2 is 20. So we're left with 20t. Algebra time. So we got 20 times t. I want to get rid of it. This is to get to 1t. So if I put 20, I get 20 over 20, which is 1 t. I do the same on both sides. Whoops, 20. 125 divided by 20 will give us t, which is, let's just say t equals 6.3 seconds. And after that, a little bit longer one, this one comes off fairly quick. Final statement. Look at your question. How long does this take? It takes the car 6.3 seconds to accelerate at a constant rate from 15 meters per second to 25 meters per second. Done. Therefore, right? Da, 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 da. Okay, question 7, exercise set 132. Suppose a planner is designing an airport for small planes. One kind of airplane that might use the airfield must reach a speed of 200 kilometers per hour in order to take off. It can also accelerate at 12 meters per second squared. If the runway is 100 meters long, can this plane reach the proper speed to take off? If not, how long must he make the runway? Well, let's before we get too caught up in the question, let's go through our routine, pick out what we need. So we have, stop that. We have a velocity here of the airplane at takeoff, so I'm thinking that should be a VF. I'm assuming a plane usually VI is 0. And we get an acceleration here. And we have a proposed displacement here. And I'm going to assume that VI is 0. Sorry to get on the plane if it's not. So let's jot these down. VI 0. VF 200 per hour. We'll have to convert that. We've got an A. That's 12. Meters per second squared. And the D displacement is 100 meters. Question mark. It's really saying, is this true? So, if we're looking at this, really, I wouldn't even test the 100 meters. I would set up the plane and see what delta D he needs to achieve his 200 kilometers an hour. And just do the calculation. If my D is less than or equal to 100, he's good. If it's greater than 100, then he needs to build it to the size that comes out of my calculation. So if I can use VF, VI, and A to calculate D, I'll be good to go. And we have one like that. This displacement equation is as follows. VF squared minus VI squared all over 2A. There it is. That'll give us what displacement this aircraft needs. So let's go up here, get some more space. So VF, oh, wait a minute. We got to calculate a new VF here. Let's do that. So let's just get this arrow away from it. Get out of the way. Okay. Actually, let's go back to the red for this. We need to convert this to meters per second. And in fact, it's 55.6. Okay. So, picking up where we left off. So VF is 55.6 squared minus 0 squared all over 2 times 12. And we're going to get, that's 55.6 squared. Let's just take this one step at a time. 5.6 squared is actually 3,091.36 all over 24. I'm going to divide that by 24 then. I get 128.8. So my displacement equals 128.8 meters. 3 sig figs. So update my displacement to 129 meters. That's the distance the plane needs to take off. So the runway is not long enough in his design of 100 meters. So his runway must be extended to 129 or longer. So at least 129 meters, or the plane is going to overshoot the runway before it even takes off. That should be your written answer. Good to go. Exercise set 132, question 8. At high speeds, a car can accelerate at 0.5 meters per second squared. How long will it take this car to accelerate from 80 to 120 kilometers per hour? So let's get a V1 or VI, get a V final. I've got an A here, an acceleration, and how long is reference to time. How far means distance. Let's jot these down. Velocity initial. Got some converting to do. It's 80.0 kilometers per hour. We're going to convert that. 80, we've converted it before. That's 22.2. Some of these are, you'll remember them after a while. Meters per second. Velocity final is 120. That converts over to the 33.3. We had that one before too. Okay, they're converted. I also have an acceleration. Acceleration is 0.500 meters per second squared. How long will it take? What time will it take? Is the question. Can we do it? I have VI, VF, A, and I want T. Is there an equation? Absolutely. Let's go to it. It's an constant. It's acceleration. Whoops. Acceleration. That's our VF minus VI over T. Minus VI over T. I believe these are squared. No, they're not. Are they squared? No. So it's change of velocity over time is acceleration. We know the acceleration is 0.5. And we know that's That's equal to 33.3 minus 22.2 all over t we're solving for. So 0.5 equals 11.1 over t. Fancy Nancy algebra. Want that t at the bottom, multiply both sides by t. What I'll get is on the left, so I get 0.5 times t is equal to 11 because these t's cancel on this side. Okay, now I need to divide both sides by 0.5 to get t all by itself. So divide 0.5, 0.5. He's monkeying on me here. 0.5, 11 divided by 0.5. Okay, now I have t equals, mamma mia, 20, oh, it's 11.1. It's 22.2 seconds. Just gonna move this a little bit. Therefore, I get it. Well, I gotta look at my sig figs, I guess. I had 3, 3, 3, so I want 3, so that in fact is my answer. Right there. How long will it take? It will take the car 22.2 seconds to accelerate from 80 kilometers to 120 kilometers per hour.